Yeah, hi, I'm Thomas, and welcome to this presentation. Today I'm going to talk about noise color influence of on escape times in nonlinear oscillators, and I'm going to present some experimental and numerical results. So this presentation accompanies a recent publication by Professor Balachandran and myself. Both we are located at the University of Maryland in College Park. And the paper it appeared in 2023 in the Theoretical and Applied Mechanics letters. So just to motivate noise in mechanical systems, so many engineering systems operate in an environment which are most appropriately addressed in the stochastic framework. So for example, here the road roughness then acting on the tire and the suspension system in the overall car is most appropriately described in the stochastic setting. Similarly, wave and wind loading acting on wind turbines has been described with the in a stochastic framework, or aerodynamic loads acting on the wind span, or similarly thermal loads on a MEMS device here. And for those kind of studies, one often resorts to white noise as the noise model of choice, which is a very convenient assumption because there's a well-developed underlying mathematical theory and many computational tools exist to tackle those kind of white noise model, to handle the white noise models. However, white noise is unphysical, and this leads to a limited qualitative comparison between numerical and experimental studies. So just to show you what can happen in nonlinear dynamical systems and noise and the noise and the interplay of those two factors, I'm just going to show you an experiment in the lab I'm working in. So this is a shaker here, which applies some kind of excitation to the oscillator, to this cantilever, which is going to be my oscillator in the upcoming couple of slides. And this oscillator behaves nonlinear. The nonlinearities are primarily induced by the tip magnets up here. And then if we now supply a harmonic excitation, we can observe multistability close to the resonance. So there is a region where we can observe two coexisting steady states. And now if we add noise, one can observe jumps between those two steady states. And this has been exploited, for example, in the stochastic resonance, for bistable energy harvesting, for localization, energy localization, and in response steering. And the goal of this talk is to present an experimentally validated study on the impact of different noise models on the escape time. So the experimental campaign is first we need to generate an initial condition inside the multistability region. To this end, we sweep up somewhere we initialize, somewhere in the outside the bistable region, and then we sweep up into the bistability region. And after we have reached the region of bistability, we will add noise. And then we observe the strain, which is measured in our case with strain gauges, and then one can observe the following. For example, so here in the beginning, we have initialized at a high amplitude state, and we see vibrations with a large amplitude. Until after about 60 seconds, the amplitude drastically drop, and then we see some low amplitude vibration pattern, which is somewhere close to the amplitudes here observed for the deterministic system. So, this transition from high to low amplitude is called an escape, and the time at which this is observed is called the escape time. And we are now recording this escape time for different noise models. And to have to get this sense of the distribution of the escape times, we repeat such experiment many, many times, about 100 times, to get a statistics of the mean escape time of for different noise models. So we accompany this experimental campaign with simulations. To this end, we need a simulation model, and we need a we're going to start with some deterministic system identification. So we take the response measured from the experiment. So this is the force response of the system. We see bistability region here. and we can fit, for example, a Duffing oscillator, classical Duffing oscillator to these measurements. And whereas the force response of those of this model now and the cross-market the measurements agree very well. So one and the Duffing oscillator has been used for similar experiments quite extensively. However, if we look closely, we see that the Duffing oscillator, for example, does not produce a second harmonic, whereas the experiment has a clearly visible second harmonic. So to alleviate the shortcoming in the model, we include a quadratic coefficient. And now adjusting the parameter values manually, we see we can obtain a good fit for the first three harmonics. So this fundamental, second, and third harmonic. So having concluded the deterministic system identification, I'm going to tell you a little bit about the different noise models utilized. So we're going to quantify the noise models in the power spectrum. The first one is the noise, the white noise, which has a flat spectrum over the whole band considered. Next model is the pink noise, which decays with a coefficient of 1, so it's 1 over f. This is also shown here on the right-hand side. Similarly, the brown noise, the Brownian noise or brown noise in the following decays with a coefficient of alpha 2, so even quicker than the pink noise, and also included here on the right-hand side. And in addition, we consider band-limited white noise with a band limit between 10 and 100 hertz. All those noise models are scaled such that they are equal in the vicinity of the eigenfrequency of the experiments, which is around 40 hertz. To obtain the correct intensity for the simulations, we looked at the power spectrum of experimental and numerical runs, and we varied the intensity of the noise in the simulations until we reached the match in the power spectrum. So we can see that for Gaussian white noise, for pink noise, we see a very good agreement between the simulations and experiments, also for the other noise models, not shown here. We see some discrepancies for very low frequencies, which can be explained by the guide, the sliding table utilized in the experiment, and also for high noise, for high frequencies where we hit the noise floor simply, which is not there in the experiments. But overall, we see that we can match the in the vicinity of the eigenfrequency, we match the simulations and the experiments quite well. So how do we simulate now the noise model? And I've told you most models, most stochastic integrators or tools to simulate stochastic differential equations are developed for white noise. But here we have a colored noise model, and we just do a little trick here. So essentially what we do, we design a filter which is driven by white noise, and the filter is designed such that the output here, N is equal to the appropriate noise model. So this will be then pink noise, brown noise, or band-limited white noise. And we just tune these coefficient matrices A, B, and C such that N follows the selected power spectrum. The next step, we enlarge the state space. So we include not just the position and the velocity of the model, we also include the filter states in the enlarged dynamical system. And then we can rewrite this dynamical system and this dynamical system into one combined dynamical system, which is then forced by white noise. So W dot here is my white noise. And now we can use tools which are readily developed for stochastic differential equations, which are forced by white noise. And in our case, we utilize a fast integration routine, which is developed for white noise. The results here, these are the different escape times for the different noise models: white noise, band-limited white noise, pink noise, and Brownian noise. We do have the simulations results in blue and the experimental results in orange here. And we can see these are kernel kernel density estimates of the escape times, and we see that those distributions overwhelmingly agree. Looking a little bit closer to the mean escape times, we see that the noise models, different noise models, do have an impact on the mean escape time. And we can see, for example, that compared to the white noise, the band-limited white noise has a larger mean escape time. This can be explained by, for example, noticing that the band-limited white noise is generated by essentially um, filtering white noise. Thereby, this decreases the energy content, and this could, for example, explain an increased mean escape time. Um, the pink noise, for the pink noise, the mean escape time is drastically reduced compared to the white noise case, and for the brown noise, we observe approximately the same mean escape time. Looking at the escape probability, those essentially confirm the observation from the previous slide. So for even any given time instance, for example, here after 10 seconds, we observe that the white band limited noise has the lowest escape probability. So this one has most likely not escaped, whereas the escape probabilities for the white noise and the brown noise are approximately comparable. The pink noise has the highest escape probability, so for any given time, this has most likely escaped after 10 seconds. So to summarize the studies, I presented experimental and simulation results on the escape times of different noise models for this experiment here. And so we obtained distributions of the escape time. We also compared the mean escape times. And the takeaway message is here that pink noise reduces the mean escape times significantly compared to white noise, which is approximately the same as Brownian noise. And then if you look at bantam with the white noise, this increases the escape times. If you're very welcome to have a closer look at our publication here. For the future, we are looking to verify the universality of the observed trends. So essentially repeating similar studies for other experimental configuration, or looking into a noise model which is inspired by an industrial or environmental process. Thank you very much for listening. If you have any questions, feel free to reach out and shoot me an email. Thank you very much.